Again, here, they were nice to draw the parent function for us. You wouldn't necessarily, well, most likely on an exam, you wouldn't get that. Okay? You would have to be able to look at this and say, I recognize that as a square root graph. And so I draw y equals the square root of x, first of all. Now I'm going to take this out and rewrite this so that my 2 is on this side. Then I check, does this one have horizontal translation and horizontal stretch, reflection, or compression? Yes, it does. Is it in factored form? No, not yet. So then another thing you would have to do this equation is factor out the 3, leaving you with x plus 1. When we go through this, here we have a vertical reflection. Here we're going to have a horizontal compression. This is going to be a horizontal translation. And this is going to be a vertical translation. Three points that you know from your square root graph. The key one is 0, 0, because that's the starting point of your graph. You also know 1, 1 and 4, 2. 4, 2 right there. They extended this graph so that you could also see 9, oops, got that point over a little bit. 9, 3 would actually be right there in between because they're going by 2's. Okay? That's something to be careful with too when you're given a graph. Notice the scale is going by 2's for the x's. And if you're moving things 1 to the left and just using the graph, can you see yourself, oh, I need to move 1 to the left, so I'll just move it there? Because that's one space. But in reality, according to the scale, that's going by 2's. I'm going to warn you right now, that happens sometimes on quizzes and tests and exams. I'm not doing that to try to trick you. But you just have to be careful with that. The reason they extended it to get to 9, 3, can you see that with the horizontal compression, you're going to have to multiply your x values by 1/3. If I use the point 4, 2, I'm going to get a fraction. That's not bad. We're going to look at what happens when you have a fraction and how you deal with that. It's not bad. It's just not as nice. So if you had the foresight to look at what's happening and choose your points, if you're going to choose just 2 points, I would choose 0, 0 and 9, 3. Those will be nicer points to use. But we'll look at what happens to 4, 2 if you chose that point. Now you can do all your reflections and compressions going from left to right together and all your translations together. So if I would do my reflections and compression together, the vertical reflection, that'll mean I'm going to multiply my y by -1. The horizontal compression means I'm going to multiply by x by 1/3. 0, 0 stays 0, 0. Again, here we're going to get the fraction, because when I multiply by 1/3, I get 4/3 and -2. And this one, when I multiply by 1/3, will give me 3, -3. Now I can do my translations together. We're going 1 left, 2 up. Fraction there. How do I go 1 left from 4/3? close. You went one right. That would have been, but the right idea. What did you do? To move 1 in either direction, you need a common denominator. 1 is 3 over 3, right? So if I'm at 4 over 3, and I need to subtract 1, well, subtracting 1 is like subtracting 3 over 3. And then you'll go to 1/3. One-third, comma, and we still need to go 2 up. This will now be at 0. And finally, this one left, will be at 2, and 2 up would be at -1. This graph isn't so busy with asymptotes, so I will graph it on the same one. -1, comma 2 is right there. 1/3, comma 0. As far as graphing a fraction is, you're just going to have to estimate. I know that 1 is halfway between these two marks, so 1/3, estimate it would be approximately there. Did you see what I did? I did the thing I warned you about. The thing I warned you about is just counting over 1 and drawing your point. But what do each of these ticky marks along here mean? They mean 2. So this point needs to be over. Can you see yourself making that mistake? Yes. In that case, it might have been better to take out one of those little graph papers and draw a separate graph, because then you probably wouldn't make that mistake drawing it on a separate graph, because then you would choose the scale, and most likely you'd choose a scale that was going over by 1s. But finally, we have the point 2, -1, which would be right here. Okay? We remember that this was our starting point. So -1, 2 will be our starting point, and that's where I'll start my graph. And when thinking about the shape, I have a vertical reflection which will reflect that red one down. And then I compress it and then translate it left and up. So this is the right shape for my final black graph. I know where my starting point is. I've labeled the points that I ended up with, and there I have the graph. If you wanted to do each graph separate, you could do the reflection. I'll show you what that looks like. You would first flip it down, which would end up looking like this. Then you would compress it horizontally. So then you would draw it like this. Then you would translate it 1 to the left. And you would draw that graph. And then finally you'd translate it 2 up. And you would get your final graph. But you would have a lot of little graphs on there, which would end up being confusing. So there we have our final graph. What is the domain and range of this black graph? The key thing for the domain and range of our black one is where this starting point is at -1, comma 2. Its smallest value is -1. So now the x values are bigger than or equal to -1. Or you could write it from -1 to infinity. And our range, it has no smallest value. It has a largest value at 2. So y is less than or equal to 2. Or you could write that no smallest value, but it goes all the way up to 2. Questions you can do from this one are 8 and 10. So yesterday we were told that there was a graph that had horizontal and vertical stretches and compressions, and to find the equation. This one's harder because it has those vertical and horizontal stretches and compressions, but it also has translations. So we start by looking at the same thing we did the other day, which We have our points A and B and A prime and B prime. So A and B on our original graph and A prime and B prime on our new graph. We're going to look at both the vertical and horizontal distances. So if we look at our vertical distances first, from A to B and from A prime to B prime, we're going to notice how it's been stretched or compressed vertically. So A is at 8 and B is at -8. So we've got a vertical distance of -16 if you go from A to B. From A prime to B prime, we go from 0, a y value of 0, down to 8. So we go down 8. And so what's happened to y values to do that? Your y values have been multiplied by a half. Horizontal distance. A to B on our original graph, we go over 2 plus 2. A prime to B prime, we go over 2 as well. Basically, that's no change, right? You can think of it that you've multiplied your x value by 1, but that's really not changing anything. Now, what the difference with this question compared to the one we had before is the one we had before, we would have been done because it just told us there was just stretches and compressions. So with just stretches and compressions, we figured that out, we would be done. In this case, we're not done yet. We're going to put in our intermediate points. If you would do this as your first transformations, because you would do your transformations first, moving from left to right, the only thing we're going to have to do is multiply our y values by a half. What's going to happen to this point A? It's going to end up at 4 when I multiply my y values by half. What's going to happen to point B at -8? It's going to end up at -4. Notice those green points don't match up with our final blue graph. We still need to move this point over and down, and this point over and down. So looking at, after we notice what our stretches and compressions are, we still need to go left 2 units and down, again, don't just count the spaces, can you see it's going by 2s? Down 4. So now we can say, I know that my compressions are a half and the x doesn't change. Then I need to go left 2 and down 4. How do I write that as a final graph in terms of f? Well, the half would be out in front of our function. We have no change for horizontal compression, but we do need to move it left 2. That will show up as an x plus 2 inside the function. And the down 4 will show up at the end as a -4. The question does say, then verify. As far as verification needs to be, you would take the 2 points that we have originally. A was 0,8. And point B was 2, -8. You would check if you multiplied y by the half, what point you would get. Then if you moved it left 2, down 4, you will find out that you will get -2, 0, which matches up with the point on our blue graph, and 0, -8, which matches up on our blue graph, and that would be how you would verify it. Question number 9 is the one you can do for homework.